This is the ELEC 1510 Logic Design Lecture 3, Video 1, an Introduction to Boolean Algebra. This is going to correspond to the textbooks section 2.2. The first thing that I'm going to talk about so that we can understand the rest of the material in the chapter is something called a truth table. So truth tables are basically just tables of zeros and ones with inputs. So for example here, inputs and outputs. There's going to be a vertical line dividing the inputs from the outputs in a truth table, and these are used to represent Boolean equations essentially. The one on the left is the truth table for the Boolean equation z equals x or y. And we know from a previous lecture that z equals x or y is going to produce z equals 1 if either x or y is 1 or if both x and y are 1. So we list all possible values for x and y. That means here x being 0, y being 0, x being 0, y being 1, x being 1, y being 0, and x being 1, y being 1. Those are all of the possible values that those two binary variables can take. And then for the outputs, z is going to be 1 here if either or both of the inputs is a 1. So that's the truth table for that equation. Now correspondingly, the truth table for z equals x and y is where, again, we list all possible values of x and y. And then the output z is going to be a 1 for only the condition that both x and y are 1. Alright, so now getting into some Boolean algebra theorems. We have the Associative Law of Boolean algebra. This says that x and y and w is equal to x and y in parentheses and w outside of the parentheses. So the order of the operations in terms of anding a whole bunch of variables is not important. So if we drew out the truth table for either one of these functions, it would be exactly the same. If you assigned an output z to either of those, in both cases the output would be the same. Now when we draw either of these as a logic circuit, we know that, say, for the equation z equals x, y, you use an AND gate with the two inputs being x and y and the output being z in order to represent that equation. Now, say for this equation, we need one AND gate for y and w, and then that gets plugged into another AND gate with x. And then the output here is z. Again, I assigned an arbitrary output z. So what this means is what was inside the parentheses is the input to the first AND gate here. What was outside the parentheses is the input to the second AND gate. Now it doesn't matter which variables we assign in which order here. So for example, now in the second setup, I could assign x and y to the first AND gate and w to the second AND gate, and we would get the exact same output. It doesn't matter which order they're in. So that's the associative law of Boolean algebra. Let me erase some of this. Additionally, that also works with the OR function. So what that means is that if we draw this as a circuit, let's see, I need two OR gates. The output of that one is going to be z. The input here is going to be x, and then a second OR gate for what's inside the parentheses are going to be y and w. Again, it doesn't matter what order I put the input variables in. So in the first case, I had assigned the single variable outside the parentheses to the second OR gate, and the two variables inside the parentheses to the first OR gate. Now I can swap those around how they're written in the second equation to make W the input to the second OR gate and the inputs to the first OR gate, X and Y, and I'll get Z out exactly the same again. The commutative law of Boolean algebra says that X and Y is equal to Y and X. So basically what that means is that if I assign an arbitrary output to these functions, Z, that means that it doesn't matter what order the input variables are in. So this seems fairly self-explanatory, but obviously when we get to much more complicated circuits, this will be helpful to know. It doesn't matter which order you put the variables in when you assign them to the gates. So X and Y here, like this, can be written like that, or I can just swap the order of them, Y and X, and that's fine as well. That also works, I should mention, with addition too, or the OR function. So X OR Y equals Y OR X. Okay, the multiplicative identity of Boolean algebra says that X and 1 is equal to X. So let's prove this using a truth table. This is basically the function X and Y equals Z. So I'm going to look at the truth table for the function X and Y equals Z, but now Y is equal to 1, and we'll prove that Z is equal to X. So I have all of the possible values that X can take, but now Y, because of Y being equal to 1, can only ever equal 1. So I have to cross out the rows where Y is equal to 0. So Y is only ever equal to 1 here. I've crossed out the other rows. And now what you can see is that when X is 0, Z is 0, and when X is 1, Z is 1. So Z is equal to X. The additive identity says that X OR 0 is equal to X. So let's prove this again using the truth table for the function X OR Y is equal to Z. Now that truth table is shown here, but now Y is going to be equal to 0, and I will prove that X is equal to Z. So I need to cross out the rows where Y is equal to 1, which is here and here. And now if I look at what Z is, when X is 0, Z is 0, and when X is 1, Z is 1. So now I've proven that there's an equivalence between X and Z, so X OR 0 is equal to X. The distributive law says that X and, in parentheses, Y or W is equal to X and Y or X and W. So this will probably come in more handy when we start drawing more complicated logic circuits. This is basically the same as the normal algebraic identity, where you distribute the multiplication to the two variables that are being added together.